consider this simple circuit. You have a voltage source, and the voltage source is connected across a resistance R, and a current I flows through it. So this is a resistive load. Now, for a sinusoidal voltage wave shape V, what is the current I wave shape under steady state conditions? So you see that the voltage wave shape is like this, sinusoidal, and importantly the current wave shape is in phase with the voltage wave shape as seen here. Now consider a pure inductance connected across the same voltage source. Now for this pure inductive load, and also for a sinusoidal voltage wave shape Vm sin omega t, what is the current wave shape expected under steady state conditions? So you will see that the current I in this case is delayed by pi by 2 or 90 degrees with respect to the voltage wave shape. Likewise, if you consider a pure capacitive load connected across a sinusoidal voltage wave shape, and then for a sinusoidal voltage wave shape Vm sin omega t, what is the current that you will expect under steady state conditions? Here in this case, you will see that the current is leading the voltage wave shape as against the inductive load where the current was lagging by 90 degrees. So the current here is leading by 90 degrees. Putting them all together, comparatively, you will expect visually on the oscilloscope for a resistive load V and I like this, for a resistive load V and I like this, for an inductive load, and this is for a capacitive load. Now take the case of the resistive load wave shape. You have voltage and current in this fashion. Now let us say you would like to plot the instantaneous power. So when you plot the instantaneous power, which is instantaneous value of V into instantaneous value of I, instantaneous value of V into instantaneous value of I, instantaneous value of V into instantaneous value of I at same time locations, you will get this power curve as shown here. Observe that at this point here power is 0, instantaneous value of power is 0 because V is 0, I is 0, and here too power is 0 because V is 0, I is 0, and at around this region power peaks because it's Vm and Im both are at max value. And observe that the power curve is having double the frequency of the voltage or current frequency. And another thing is that the power curve is having an average value is shifted up. So if you now only consider just this power curve and remove all the other waveforms, you will see it's something like this. This is the power curve and there is an average value P average. So this is a visualization that you should expect for any resistive load wherein the source is a sinusoidal source. For an inductive load where the wave shapes are like this, voltage wave shape, current wave shape, multiply instantaneous values of the current and instantaneous values of the voltage at the same time points, you will get the instantaneous power curve like this, the blue waveform. Observe that this is having a 0 average. If you remove out the voltage and the current wave shapes, you will get only the power wave shape for the inductive load, which is like this. The average value is 0, whereas the instantaneous value is double the sine frequency as the fundamental. In a similar manner, if you look at the capacitive load waveforms, voltage, a leading current waveform like this, if you multiply the instantaneous values of the current and the voltages, you will get the power curve in this fashion. This is the P is equal to VI, instantaneous power curve. Here again, if you remove the voltage in the current waveforms, it becomes clear that the average power is 0. Comparing all the three cases, you should visualize that on any oscillogram. For a pure resistive load, this will be your power curve and the average power. This would be the power curve for an inductive. Average power is equal to 0. Average power is equal to 0 for the pure capacitive load also. Now, consider the same voltage source Vm sin omega t applied across R and L hybrid impedance consisting of resistance and inductance. Now, the voltage wave shape is shown like this. The current wave shape can vary with different lags. It can be 0 when it is purely resistive, and as the value of resistance keeps decreasing and inductance increases, you will see the phase shift starts moving like that to what is when purely inductive. So if you look at the power curve, for the case when R is equal to 0 ohms, it will look like an inductive visualization. Average power is 0, and this is the instantaneous power curve. Now keep increasing the value of R, then it becomes an RL load. So as you start increasing the value of R, you will see that the entire power wave shape shifts up and there is an average power available. And that is the active power or the real power that gets dissipated because of the resistor R. So as it starts moving up at a point, you will see that as the value of the inductance becomes 0, the RL load tends towards the resistive load, and you will see a wave shape like this where the average is given by Vm by 2. Likewise, for the RC load also, where you are having R and C connected, except for the phase shift which changes from lag to lead, you will see that as the value of R increases, the value of C decreases. You will see that it starts moving in this fashion, going more towards the pure resistive type of load. Some remarks that we can make at this point in our discussion is that the average power is maximum only for pure resistive load. For any other type of loads, any other combination of the loads, the maximum power is less than Vm by 2. Let us now discuss how to measure power factor. We would like to measure power factor only using the wave shapes as seen on the oscilloscope, the voltage and current wave shapes. Let us begin with sinusoidal wave shapes, sinusoidal voltage and current, and then move on to the nonlinear wave shapes of rectifier capacitor filter circuit. Now on this graph, let us put in the voltage, sinusoidal voltage wave shape. Then let us take an arbitrary delayed current wave shape. So there is an arbitrary phase delay of phi, which means it's an RL load. Now this, when you multiply the instantaneous values of the voltages and the currents, you would get the instantaneous power curve, and this would look like this. Observe that the power goes negative here. This is because the voltage is positive in this region, current is negative in this region, the power is V into I, and therefore it has to go negative. At this point voltage is 0, current is negative. At this point current is 0, voltage is positive. So therefore the power crosses the 0 point at this point. Likewise here also, voltage is 0 at this point, power is 0. Then voltage goes negative here, current is positive. Therefore, the power is negative in this region till this point when both current and voltage goes negative, and from here onwards power becomes positive. So this is the power curve having double the frequency, the voltage or the current. So this power curve will have an average value like this as shown. Now this negative part which I am showing shaded here, this is the negative power, which means that it is put back into the source. It is taken from the source and then put back into the source, and the positive part is pushed into the output. So the positive part, so this would be the active power pushed into the output, and this negative part is the part, the reactive part, which is put back. So this is the power curve showing the positive and the negative aspects, the active and the reactive part. Now if you compare with an RL load, R and an RL load, you will see that the current waveform here is in phase, and that is having a phase shift of phi. And the power, instantaneous power curve here and the instantaneous power curve for the RL load is like this. Now the averages, look at the average. The average for the R load is much higher than the average for the RL load because of this negative portion which gets subtracted from the area when you are integrating. Let us remove the voltage and the current waveforms so that it becomes clear. Let us move this waveform up. I am going to compare this RL load with respect to a pure resistor, which implies that by comparison I am going to get the power factor, which is basically which is giving me a measure of this RL load, how close it is to a pure resistance. So let me call this as PR, the average of a resistive load, pure resistive load, and this we can call it as P load, is the RL load. So now what is power factor for this load? We define that power factor is a measure of the degree to which this RL load matches to that of the pure resistance. Power factor, let us say we define it as P load divided by the reference pure resistive load power, which is PR, all else being same, the amplitude of the current and the amplitude of the voltage. So this is the definition that we will be using, and which will give you the measure of the closeness of any given load to that of a pure resistance. When PF is 1, that is P load and PR are same, which means these two values are same, then we say it's a resistive load, or the load is equivalently same as that of a resistive load. When PF is 0, that is when P load is 0, then the load is furthest away from being a resistor, it is a reactive load. So now this definition, PF, which is P load by PR. P load is the average power of any given load, and this can be measured from the voltage and current waveforms of the oscilloscope itself. PR is the average power of a resistive load for the same voltage and current magnitudes. This is the important clause there. So as power is an average quantity, so this measure definition should be valid for any voltage and current wave shape.